3 years ago, I started working on a rendering engine. I was given advice at the time by a random YouTuber to start with either DirectX 11 or OpenGL graphics APIs, and for a long time I was dissatisfied with my decision of using DirectX. The main reason for this was my ever-increasing hate for Windows and the hope of being able to use Linux someday. I want my engine to work on all platforms, not just Windows. Bill Gates is personally holding me hostage from going multi-platform. All that ends today, because we are going to Indonesia? This is Vulkan. Vulkan is one of the most modern, publicly available cross-platform graphics APIs. It is explicit by design, giving precise control over everything: memory, synchronization, and execution. Vulkan is designed for modern hardware and modern engines, hopefully someday ours. Partly due to how ambitious Vulkan is, it is also infamous for being very hard to learn, especially for amateurs like myself. But I don't care. So let us begin. Let's start by temporarily deleting everything. I will later be using most of the code I have in the engine currently, as it is not platform dependent. Anyway, since I will be rewriting the entire rendering part of the engine due to using Vulkan as a rendering API, I thought it would be a good time to quickly fix some build system and architecture issues as well. We will go into specifics later. For now, I set up some template code with glfw library that creates a window, and it was a perfect time to start testing on Linux to make sure my new build system even works. I have Linux Mint installed on my laptop, as I'm only a casual Linux enjoyer. I pulled the project on my Linux Mint laptop, installed CMake, the CLang compiler, and Vulkan software development kit. I will go into more detail about the new build system soon, but for now... Now finally, the moment of truth. Will my empty window run on Linux? Yes, it will. My dreams of escaping Bill Gates might come to reality soon. Testing on two different computers can get pretty annoying, and maybe you have noticed, but actually I am using the same mouse and keyboard to test on both computers. And that's thanks to our today's sponsor, Synergy, a tool that lets me seamlessly use multiple computers with the same mouse and keyboard, even across different operating systems. After installing Synergy on both computers, they automatically detect each other. I set the layout once, and then I can move my mouse between machines, use the same keyboard, and even copy-paste between them. This is extremely convenient for testing my engine on both Linux and Windows. Synergy works on Windows, most Linux distributions, and Mac OS, and everything runs locally over your home network, no cloud involved. Honestly, this tool is amazing and was very easy to set up. I will definitely be using to test my engine on both Linux and Windows. If using multiple computers is something you do too, make sure to check out Synergy in the video description below. Huge thanks to Synergy for sponsoring this video. As I mentioned before, I decided to fix some build system issues with the engine. The first thing I didn't like was the dependency on Visual Studio project files. It is not a good experience to use Visual Studio on Mac or Linux, so we will not rely on it anymore. I will be using Visual Studio Code for writing code, and will add linting support for it. But in general, the engine will not depend on any IDE. The second issue we had was importing all libraries directly into my repository, which is not ideal. It would take lots of time to update package versions manually each time, so we need everything regarding packages to be automated. As our build system generator, we will use CMake. It will fetch all needed packages, configure compiler, linker, and other settings, and output Ninja project files. Ninja is the build system we will be using. It is a modern build system that allows for very fast incremental builds that will work the same on all platforms. The compiler I chose is CLang, mainly because it works on all platforms and is very easy to install on Linux. Unfortunately, on Windows we need MS Build as a prerequisite, which comes with the Visual Studio installer. I just can't escape him, just let me out. Perfect. Now finally onto the Vulkan part. For that I will be following a guide found in vkguide.dev. This guide was recommended to me by a friend, and while a little outdated, I found it very useful. This guide offers basic explanations and links if you want to dive into topics deeper. I will be following the guide at least until we set up basic 3D rendering, and maybe even after that. As I mentioned before, Vulkan is infamous for being very difficult, and one of the biggest challenges is the setup. Because Vulkan is extremely explicit, even rendering a single triangle on the screen can require almost 1,000 lines of code. To reduce this boilerplate, as suggested by the guide, I will be using an external helper library called VK-Bootstrap. VK-Bootstrap provides reusable setup code for creating rendering devices, swap chains, drawable surfaces, and other essential Vulkan objects, allowing us to focus more on how rendering works rather than spending all our time on initialization, which even with the help of this library was abysmally long. With that in mind, I think it is a good idea to revisit how basic rendering works. I will oversimplify things, but at a high level, we only need to be aware of 4 concepts. First, we need a device. In Vulkan, a device is a virtual representation of a physical GPU. We issue draw commands through this logical device, which are then passed to the driver and finally executed by the physical GPU itself. You can think of the device as the main interface we use to communicate with the GPU. The second important concept is the swap chain. For now, we can think of the swap chain as a collection of images that we render into. These images are specifically meant to be presented on the screen. Rendering happens in multiple stages and takes time, but as users, we never see partially rendered frames, we only see complete images. This is what our swap chain is for. At runtime, the application has 2 or more images. While one fully rendered image is being displayed on the screen, another image is being rendered in the background. Once rendering is complete, these images are basically swapped. Once again, a little bit oversimplified, but you get the point. This process repeats forever until the application is shut down and allows to render each frame in the background fully, and display it only after it has been fully rendered. The third concept is command submission. Images don't magically appear on your physical screen. In Vulkan, we specify what we want to draw and how we want to draw it, and then submit this information as commands to a queue, and the GPU executes them asynchronously. Unlike older graphics APIs such as DirectX 11, Vulkan does not like being told when to do things. Everything is recorded first by us and executed later by the GPU, whenever it feels like it. Finally, after an image has been fully rendered, we present it. Presentation is the final step where we ask the system to take a rendered swap chain image and display it on the screen. Vulkan also exposes explicit synchronization mechanisms such as semaphores and fences, and a whole shitload of other complicated concepts I don't understand. In APIs like DirectX 11, this was handled automatically by the driver and spoon-fed to the GPU, whereas Vulkan developers assumed idiots like me wouldn't dare touch this library. Oh, I will show them. At this point, I was blindly copy-pasting code, slowly crawling through the guide. With the help of a couple of friends who also do Vulkan development, I managed to fix some errors regarding semaphores, courtesy of a new Vulkan version. An important topic we have not touched yet, since it seems I'm just rewriting everything, is what will I do with the DirectX engine? Well, I will reuse it. Minus the rendering code, everything can be reused, since the Vulkan renderer is using C++ as well. After I am able to perform basic 3D rendering, I will port the entity component system to the Vulkan engine, with some adjustments of course. Another important thing to do is to set a goal for the Vulkan renderer. Instead of randomly implementing new features, I want to set a final goal and work towards it. During early stages of DirectX 11 development, I was playing around with gravity simulations, and I would really like to create something like this, but more polished. I would like to create a small planetary system and simulate millions of particles, maybe add some sliders for physics parameters, and to create sort of a sandbox for all of this. Main point here is to test the entity component system combined with Vulkan batch rendering to prove I can simulate millions of particles at a single time, not just render them. For now, I will be slowly crunching at this Vulkan tutorial. It will take some time, but I'm confident that I will be able to achieve something in the end. That's all I have for you today, you absolute beast who watched till the end of the video. I hope you found the video interesting and maybe even made some code gains yourself. If you enjoyed this video, consider dropping a like and subscribing. See ya! Bye. 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 Bye 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 bye.